Hello everyone. On this video we will be going over polar coordinates. Okay, so let's do a quick explanation as to what we mean by polar coordinates. Okay, so to do that we're going to look at how we normally explain a point on a plane. Okay, so we usually represent a point on a plane by using, there we go, Cartesian, or in some cases, depending on the textbook you use, they may call it rectangular coordinates. Okay, so for example, you have the point 2, 4. That's your ordered pair, your x is 2 and y is 4. Okay, so you have your x and you have your y. So if you go 2 over and 4 up, 1, 2, 3, 4. To plot that point, you just go to the right 2 and up 4. There you have your 2, 4. Okay, so what we're going to do is we're going to use a different method of getting to that same point. And that method is called using the polar coordinate system. Okay, so the polar coordinate system has an ordered pair that we will call r theta. So the Cartesian has x, y, polar coordinate system has r theta. And that point starts at the pole, and the pole is just the the polar version of the origin. And has a polar axis, which is just a ray starting at the origin. So if you're at the origin and you're looking at your ray, basically it's your x-axis. So it's a ray starting at the origin. Alright. Okay, so we're going to go ahead and go to our next page. If you are still writing, feel free to press pause, but we're going to go ahead and move on. Okay, so to give a better explanation as to how we can reach our Cartesian, from Cartesian to polar axis or polar conversion, let's say if we let uppercase P represent any point on a plane, and if we let lowercase r represent the directed distance from the origin. And so what we'll do is we'll call the origin just uppercase O. And that's to the point that we will have our P. And in addition, what if we have our theta be a distance or the angle from the polar axis to the line? Okay, so we'll write that down also. So that theta, okay, is the angle from the polar axis. There we go, to the line from O to P. Uh-oh, sorry about that. Okay, so to get all of this into a nice little picture form, let's say if we have our origin, remember that's our uppercase O, so that's where we're starting, and a ray leading from the origin, that's our polar axis. Okay, and we're looking at some point that we'll call P. So this will be the directed distance from O to P. And remember, from here to here, this is your O to P. Okay, so this is how this particular explanation would look as a visual aid. Alright, and let's say just for a little extra, oh, forgot my theta. This is your theta. Okay, so what if we also had some point P, O here, and this is our directed distance. If this is our radius, or you can say radius, but it's really just R, then going in the opposite direction would be your negative R. Okay, so this is kind of a visual explanation as to how we would get to our point. So if this particular point is our x comma y on a Cartesian plane, then it's just our theta to get to that very same point. Okay, so let's take a look at the properties. Okay. Let's say if R is a negative value, then negative R theta and R theta lie on the same line. So they're on the same line through the origin. And is the same distance from O. Uh-oh. Okay, so that means if we go to our R theta, then negative R theta is the same distance. Okay, so let's look at another property. Let's say if your point P, that's right here, let's say that P is equal to the origin. Then R is equal to theta, R is equal to 0, and 0 theta represents the pole. For any value of theta. Oh, this just means for any or for every. It's kind of like an upside down capital A. Okay, so what if our point that's here, what if that's actually equal to the origin? So the point and the origin is the exact same space. So of course your distance is going to equal 0 because they're at the exact same spot. Okay. We have another property. We know that Cartesian coordinates are unique. So if you go to the ordered pair 2, 4, there's one way to get to that 2, 4. X is 2, Y is 4. There's one value there. But for a polar coordinate, that point is not unique, which means you can get to that point an infinite number of ways. Okay, so Cartesian coordinates are unique, but polar coordinates are not unique. All right. Okay, so what we're going to do is we're going to take a look at a few examples, kind of give us an idea of what our property will look like here. Okay, so if you're still writing, feel free to press pause, but we're going to go ahead and move to our next page. Let me pull that down. All right. Okay, so to give you kind of an idea, if we have r theta, then that's the exact same as r theta plus 2 pi, or r theta plus 4 pi. Okay, so you have r, and you have theta plus 2 n pi. Okay, and again, I'll give you an example of how that would look. So hopefully it would make sense. Okay, same way if you have r theta, that's going to equal negative r, and theta plus 2n plus 1, put that in parentheses, times pi. And that's for any number that's an integer. All right, so let's write out a couple of examples to give you an idea of what that particular property would look like. Okay, so for example, let's say for polar coordinates, we have 0. Remember, this is pi over 2, pi, 3 pi over 2, and 360 for a complete circle, or 2 pi. Okay, so let's say if we have this particular point here, okay, where the distance from the origin to this point is 2, and from the polar axis you have a theta. Look, theta. Well, this is our theta. We'll call that theta, and this is our pi over 3. So our theta is pi over 3. Okay, if you think about it this way, if you go out 2 and swing it up, you'll hit that point. But what if you keep swinging? And you just get that and you keep swinging 2 pi. So that's right back at the same spot, because 2 pi is just a complete circle. So that will be equal to 2 and pi over 3 plus 2 pi. Or you could keep going again. 4 pi, 6 pi, 8 pi, 10 pi. You can keep going a full circle over and over and over, and you'll always hit that spot. So that's when you end up with 2 plus pi over 3 plus 2n pi as your actual solution. If you just put 2 and pi over 3, that's a solution. Okay, that means that's one of an infinite number of solutions. So your complete answer would be 2 pi over 3 plus 2n pi, if that's what is being asked for. If they ask for a solution, you can put that. But if they ask for a more detailed solution, you'd put this. Okay, so now let's look at this particular property. Move that up a little bit. Okay, so let's say, for example, okay, so we have our x and we have our y. Oh, before we do that, let's say if we have this same point, let's use the same point. There we go. Say 2 pi over 3. Okay, so now we're looking at that same point, but we're looking at this one. So negative r, and I'll put that here, negative r, theta plus 2n plus 1 pi. So basically an odd number times pi. Remember, that's for any integer. Okay, so if you think of it this way, negative r. So that would be negative 2. So negative 2 would be this way. But if you circle back 1 pi, boom, pi is a straight line, so you're right there. What about 3 pi? So if you go from this point and you go 3 pi, so you have 1 pi, 2 pi, 3 pi, so you end up there. Okay, so to get to this point, going in the opposite direction, you just multiply or add your theta to an odd number times pi, and you'll always end up right there. Okay, so that means that 2 pi over 3 will equal negative 2, and your theta is equal to pi over 3 plus 2n plus 1 pi. Okay. Alright, so let's look at one more quick example. Oh, if you're still writing, feel free to press pause. Alright, so let's move on to our next example. Okay, so what if we have, okay, so we have our, I was about to write x and y out of habit. So pi over 2, pi, 3 pi over 2. Okay, so what if we have the point, let's say 3 and negative pi over 6? Okay, now the thing about negative theta angles is they move in the clockwise direction. So if you're looking at this point here and your theta is negative, then this point here would be your 3 and negative pi over 6. Okay, that's because negative theta angles move in a clockwise direction. Okay, so negative theta angles move clockwise from the polar axis. Okay? All right, hopefully that makes a little bit of sense. Okay, so now we're going to look at how to convert from a rectangular coordinate system to a polar coordinate system. All right, so again, if you're writing, feel free to press pause. But we're going to go ahead and move on to our next page, which is coordinate conversion. Okay. So for any value of t greater than 0, you have trigonometric functions. Imply that tangent is sine over cosine, or y over x. You found that out from trig. Okay, now cosine of theta. Remember, x is your cosine of theta, but if you have a radius bigger than 1, is x over r. And sine of theta is equal to y, or if your radius is not 1, y over the radius. Okay. Now, if r is less than 0 or it's negative, you have the same relationship. Okay. Okay, so now we're going to look at the relationship between r theta and rectangular coordinates. The relationship between r theta and rectangular coordinates. All right, so what we're going to do here is we multiply both sides of cosine theta equals x over r. If we multiply both sides by r, we end up with x equals r cosine theta. Same thing with sine theta. If we multiply both sides by r, we end up with y equals r sine of theta. Okay, so as long as you have your r and your theta, you can solve for x and y. Okay. Now, if we have our, we kind of write that tangent of theta equals y over x. Of course, if we apply tangent inverse to both sides, we have theta equals tangent inverse of y over x, and r squared equals x squared plus y squared if we're looking at converting for our theta and our r. Of course, we just have to square root both sides. All right. So we're going to use what's in this box to convert from polar to rectangular and from rectangular to polar. All right, so if you are still writing, feel free to press pause, but we're going to go ahead and go to our first example. All right, so let's say, for example, if we have from polar to rectangular conversion. Let's say for problem A, we have for the point 2 pi. Let's say we wanted to convert to rectangular, which we'll call x comma y. And for problem B, let's say we wanted to convert square root of 3 pi over 6 to rectangular, or x comma y. Okay, so these are both asking to convert polar to rectangular or polar to Cartesian, whichever way you want to say it. Alrighty, so let's look at problem A. Alright, so we know that our r theta is 2 pi. Okay, so that's our r, and that is our theta. Okay, so we know that x is equal to r cosine theta. Okay, so our r, which is equal to 2, and cosine theta just becomes cosine pi. Alright, so since cosine pi is equal to -1, that's 2 times -1, which is negative 2. Okay, so we see that y is equal to r sine of theta. Again, our r is equal to 2, so we have 2 sine of theta, which is sine of pi. Now, sine of pi is equal to 0, so we have 2 times 0, which is 0. So that means that our polar coordinate of 2 pi has a rectangular coordinate of negative 2, 0. Okay, so that's all you do. You pick your rectangular coordinates there, and you plug in your r and your theta. Okay, so let's look at problem B. Let's say here we know that our r theta is equal to square root of 3 and pi over 6. Alright, so what I want you to do here is I want you to press pause and solve this one on your own. Alright, so I'm assuming you press pause and work this one out. You do it the same way this one was done up here. You have x equals r cosine theta, which is r is equal to square root of 3, and your theta is pi over 6. So that becomes square root of 3 cosine of pi over 6. So that's square root of 3 times cosine pi over 6 is square root of 3 over 2. So that gives us 3 over 2. Okay, so same thing with y. Y is equal to r sine of theta, which is square root of 3 sine of pi over 6. Alright, so sine of pi over 6 is 1/2. So that's square root of 3 times 1/2, which is square root of 3 over 2. Let me straighten that out. There we go. So we can see that our final answer, square root of 3 pi over 6, has the rectangular coordinate of 3 over 2 square root of 3 over 2. Alright, so pretty straightforward plug and chug there. Okay, so remember, this is from polar to rectangular. Uh-oh, move that down. This is polar to rectangular. Okay, now we're going to look at how to convert from rectangular to polar. Okay, so if you are still writing, by all means, feel free to press pause. But we're going to go ahead and move on to the next couple of examples. Alright, so let's say, for example, again, this is rectangular to polar conversion. Okay, let's say for the second quadrant. Okay, and a lot of times this is very important to know which quadrant you're in, and I'll show you why in a minute. Okay, so we want to convert -1, 1 to a polar coordinate. Alright, so starting off, we know that theta equals tangent inverse of y over x. Okay, so we have we know that negative 1, 1, our point, that's your x, and that's your y. Okay, so this is actually equal to, well, theta is equal to tangent inverse of 1 over negative 1, which is tangent inverse of negative 1, or theta equals 3 pi over 4. Okay, so we have our theta. So convert from x, y, we have our theta. Now we just need our r. And it doesn't matter which one you do first. R squared equals x squared plus y squared. Okay, so in other words, r squared equals x squared. So you have negative 1 squared plus y squared. 1 squared. Okay, so r squared equals 1 plus 1. So in other words, r squared equals 2. We square root both sides. R equals square root of 2. Usually positive and negative, or negative square root of 2. But we know that the distance isn't negative for this particular one because it's in quadrant 2. Okay. Okay, so we know that negative 1, 1 converts to square root of 2, 3 pi over 4. So your xy converts to your r theta. Okay, so hopefully that makes sense. Okay, but now let's take a quick look to see why the quadrant was important. Alright, so let's scroll up a little bit. I'll leave the answer visible to you. Okay, so just as a quick note, the quadrant is very important since negative 1, 1 and 1, negative 1 will both give theta equals tangent inverse of negative 1. Okay. So as long as we know that our point is in quadrant 2, we have a better idea of what our theta would be. Okay, so let's show this here. So we have our x and we have our y. Okay, they gave us negative 1, 1. So this is, let's say this is negative 1, 1. Okay, so let's say if we didn't know what quadrant it was in. So 1, negative 1. So we have 1, negative 1 here. Remember, this is quadrant 1, quadrant 2, quadrant 3, quadrant 4. Okay, so we know just by the fact that it's in quadrant 2 that your theta is 3 pi over 4. But if they didn't tell us that it was in quadrant 2, it's quite possible that tangent inverse of, let's say, 1 over negative 1 can be mistaken for tangent inverse of 1, negative 1 over 1. Okay, which is a completely different theta if you make a mistake and put this in. Okay, so you don't want to make a mistake and put in the wrong theta. That's why you want to pay attention to which quadrant you're in. All right. So let's say, oh, if you're still writing, feel free to press pause. But we're going to go ahead and go to our next example. Alrighty. Oh, my pencil lead is kind of shrinking. Let me get a little bit of extra here. Alright. Thought I had enough, but apparently I did not. So I'll get that and we can continue. There we go. Let's say if we wanted to convert our xy to the polar coordinate 0, 2. Alright. Okay, now the difference is here, to a polar coordinate. Okay. Now the reason I pointed this out is because whenever one of your rectangular points is 0, especially if it's x, that can cause a problem. Okay, so we can't use, oh, this is just a quick note. Can't use the formula since, okay, so if you have the point 0, 2, remember, that's your y, that's your x. Okay, so you have tangent inverse of y over x equals tangent inverse of 2 over 0. So you all know that if you have a denominator of 0, then everything is going to go into chaos. Okay, you can't have a denominator of 0. Okay, so one way to approach this is to draw this on a graph. Okay, so if we draw it, point on a polar graph. Okay, so we have 0, pi over 2, pi, 3 pi over 2. Okay, now we just plot our point. So if we have 0, 2 here. Okay, now everything you need to know to convert that is right at that point. Okay, so we see here, 1, that our theta for that point is 0, 2. I mean, it's pi over 2. Okay, so 1, because the point 0, 2 lies on the positive y-axis, we know that theta is equal to pi over 2. Okay, now if the point was right here, then our theta would be pi. If our point was right here, then our theta would be 3 pi over 2 or negative pi over 2. Okay, so it all depends on which, I guess you could say, quadrant line or between quadrant line these fall on. Now if your point was here, then your theta would be equal to 0. Okay, but just so happens in the positive y-axis, so our theta is pi over 2. Okay, now also we know that this point is 2 units from the origin. Since it's 2 units from the origin, we know that r is equal to 2. Since it is 2 units from the origin, we know that r is equal to 2. Okay, so we have our coordinate points. We know that 0, 2 converts to our r theta equals 2 power 2. Okay, like I said, it's one of those things where, especially if x is equal to 0, you might want to try it using this method, because you will always end up with that denominator of 0, which can confuse you if you don't think to use this little step. Alright, so hopefully this video made sense, and I will see you on the next video.